Chocolate begins here. Cocoa pods are harvested for their beans, which contain the fats and solids that will later define every bar's chemistry. Inside each pod are cocoa beans surrounded by pulp. At this stage, flavor does not yet exist. Fermentation triggers chemical reactions that create chocolate's future flavor. Without this step, time and temperature matter here. If fermentation is rushed or uneven, bitterness is locked in forever. Drying removes moisture and stops fermentation. Too much moisture later causes mold. Too little, once dried, the bean's chemistry is fixed. Nothing inside the factory can correct poor preparation here. These beans now travel globally. Every factory step that follows depends on what happened here.
Once inside the factory, cocoa beans are treated as a chemical input. From here on, every variable is controlled.
Cleaning removes foreign material. Any contamination left here will grind into the chocolate permanently. Beans are sorted to ensure even roasting. Uneven size means uneven chemistry later.
Roasting begins flavor development. Heat transforms the bean's internal chemistry. Temperature and time are critical. Too hot destroys flavor. Too cool leaves acidity locked in. Cooling stops the reaction instantly. If roasting continues uncontrolled, chemistry breaks down. Once roasted, the bean is chemically ready. The next step isolates what will actually become chocolate.
After roasting, beans are cracked open. This step separates what will become chocolate from what must be removed.
Cracking breaks the bean without crushing it. Too much force damages flavor solids.
Each cracked bean contains shell and nib. Only the nib carries chocolate chemistry.
Airflow removes shells using weight difference. This separation must be complete.
Shell fragments create bitterness and grit. If they remain, the texture is ruined forever. What remains are cocoa nibs, plum, concentrated flavor, fat, and chemical potential. From this point on, heat will unlock cocoa butter. Chemistry now dominates the process.
Cocoa nibs are still solid. Grinding is where chocolate first becomes fluid.
Mechanical force breaks the nibs, while friction generates heat. Cocoa butter melts naturally. This fat is what allows chocolate to flow.
At this stage, cocoa solids and cocoa butter combine into cocoa mass. Temperature must stay controlled. Overheating damages fat structure permanently.
The mass must remain homogeneous. Separation here destroys consistency later.
Once liquid, chocolate becomes sensitive. From here on, chemistry errors multiply quickly. Cocoa mass enters blending tanks while still warm and fluid. From this point forward, chocolate is no longer just cocoa, it becomes a chemical mixture. Sugar is added first. Its particle size and ratio determines sweetness, viscosity, and how the chocolate milk solids are introduced carefully. Too much changes fat balance. Too little alters texture and flavor permanently. Cocoa butter controls flow and crystallization. This fat ratio will later decide whether tempering successfully. Mixing must be aggressive but controlled. Every particle must be coated in fat, or at this moment, viscosity is checked. If the balance is wrong, no later step can correct it. Once blended, the recipe is locked. Refining will improve texture, but it cannot fix chemical mistakes. After blending, chocolate still feels rough on the tongue. Refining is where texture becomes measurable and permanent. Refiners force chocolate through tightly controlled gaps, breaking particles down again and again. Particles must fall below the tongue's detection limit. If they do not, chocolate will always feel gritty. Refining creates heat through friction. Temperature must stay controlled, or fat chemistry begins to degrade. Each solid particle must be fully coated in cocoa butter. Without this, later crystallization will fail. At this point, texture is locked. No future step can remove roughness once refining is complete. Now smooth, the chocolate moves forward. What remains is flavor balance and moisture control.
After refining, chocolate is smooth but chemically unfinished. Conching is where flavor is stabilized over time.
Conching applies continuous movement for hours. This exposes chocolate to air in a controlled way. Moisture is slowly removed. If water remains, chocolate thickens unpredictably and spoils. Acidic compounds evaporate here. This is what softens harsh flavors created during fermentation and roasting. Temperature must remain stable for hours. Too hot damages fat chemistry. Too cool stops. When conching ends, flavor and flow are locked. No later step can remove acidity or moisture. Now chemically balanced, the chocolate faces its most dangerous stage. Tempering will decide.
Tempering is where chocolate becomes usable. This machine controls how cocoa butter crystallizes.
Chocolate is first heated to erase all existing fat crystals. This resets the system completely. It is then cooled carefully to allow only stable crystal forms to begin forming. Reheating removes unstable crystals while preserving the one that matters. Only crystal form 5 survives. This single structure gives chocolate its shine, snap, and melt. If tempering is wrong here, nothing later can fix it. The batch must be remelted or destroyed. Once tempered, time is limited. The chocolate must be shaped before crystals destabilize.
Once tempered, chocolate must be shaped immediately. At this stage, the fat crystal structure is correct, but still vulnerable to disruption. Each mold receives an exact amount of chocolate. This controls weight, thickness, and cooling behavior later.
Vibration forces trapped air out. If bubbles remain, they weaken structure and distort the finished bar. At this point, the bar's final shape is defined. Any surface flaw will remain visible forever. Alignment ensures even cooling. Misalignment causes uneven crystal contraction and hidden cracks. Inside the mold, crystallization continues silently. This is where chemistry stops and structure begins. From this moment forward, nothing can be corrected. Cooling will either preserve perfection or...
After shaping, chocolate enters controlled cooling. This stage determines whether tempering survives or collapses.
Cooling must happen gradually. Rapid temperature drops create stress fractures inside the chocolate. Inside each mold, cocoa butter crystals continue growing into their final structure. Humidity is controlled carefully. Moisture causes sugar bloom, a failure that cannot be reversed. As chocolate contracts, it releases cleanly from the mold. This is proof that crystallization, before handling, temperature is equalized. Sudden warming would destabilize the crystal structure. Cooling is complete. What happens next will reveal whether chemistry was controlled perfectly forward or not.
Demolding is the first real test. If crystallization failed, the bar will stick, crack, or deform immediately.
A clean release confirms correct tempering. Poor release exposes hidden chemical mistakes. Gloss is not cosmetic. It proves the cocoa butter crystal structure formed correctly. The snap reveals internal order. A dull break means unstable crystals and inevitable shelf failure. Weight and thickness confirm molding accuracy. Errors here cannot be trimmed or corrected. Rejected bars are isolated immediately. Once solidified, chocolate cannot be repaired. Only bars that survive every test move forward. Chemistry has now proven itself.
Packaging begins immediately. Chocolate chemistry is stable, but still vulnerable to air, moisture, and heat.
The first layer blocks oxygen and light. Without this barrier, cocoa butter degrades quickly. Sealing is precise. Any gap allows moisture inside, triggering sugar bloom and fat migration. Secondary packaging adds physical protection during transport and storage. Every package is inspected. A damaged seal compromises months of chemical control. Cartons protect the internal environment and prevent temperature shock. Once sealed, chocolate cannot be exposed again without damage. Once packaged, chocolate is chemically complete. From here, preservation depends on controlled storage conditions. Heat softens fat crystals. Humidity triggers bloom. Storage conditions now protect months of precision. Damaged packaging is rejected. Chemical stability cannot survive broken protection.
Transport vehicles maintain temperature. Even short heat exposure can undo tempering.
On the shelf, chocolate faces light, warmth, and time. Packaging is its only defense. When unwrapped, the result of every factory decision becomes visible instantly.
A clean snap and smooth melt confirm perfect chemistry tware, from farm to factory to consumer.